So, we will continue our discussion on mathematical modeling, and we have covered the two examples of lumped parameter model. The first one was the simple liquid storage tank, and the second is the starred tank heater. So, next we will add a different feature, that is, first it is isothermal continuous starred tank reactor. Right. So, you see that here the temperature remains same, we have the stirrer. So, as it is stirred, concentration in the reactor only depends on time, right? That is, Ca is a function of time only. So, we have the outflow rate F Ca, inflow it is Fi Cai, and a reaction minus Ra represented by a first order kinetics, let us say it is taking place. Okay. So, first let us not discuss about the order. Let us say the specific reaction rate, where specific reaction rate is defined as the Na dt reaction, which is basically the rate of disappearance of moles of A per unit volume of this reactant. Okay. And this is volume, and this is the volume of the reactant here. So, what we are going to use first is the let us also write the assumption side by. The first we will write that ddt of rho into V, rho I Fi minus rho into F. So, our first assumption will be incompressible flow or incompressible system, right. So, dV dt equal to Fi minus F. So, that is equation 1. We cannot further simplify it upon writing this V dagger as A into H, because we have a curved surface here. So, the level in the tank actually for different points of the base will be different. So, that is why we are writing it in terms of the total volume of this reactant. Now, next it is a component balance. So, ddt of V into Ca, Fi Cai minus Fca. Then see here that Na decreases with time, as the reaction taking place is A giving product, right. So, dNA dt, we will see it in reaction engineering, is negative. So, minus Ra is positive, right. Minus Ra is positive because we are including a minus sign here. So, we will write it as minus of minus Ra into V, right. So, minus of minus Ra into V is simply with this minus sign, or this minus of minus Ra into V, this entire term is basically dNA dt reaction, with a minus sign, right. So, this is positive because Na decreases with time, and minus of minus Ra or minus of this will be negative. So, here if I split this into two derivatives, now you see dV dt equal to Fi minus this F. So, V dCA dt Fi minus F so this Fa, FCA and FCA cancels out, finally giving you the equation V into dCA dt Fi CAI minus CA minus of minus RA into V. So, this is 2. What you can do, we can apply the rate law considering the kinetics of reaction. Let us say it is a first order reaction. Okay. So, this is V into dCA dt Fi CAI minus CA minus K into CA into V. So, that is equation 2, and dV dt equal to Fi minus F, that is equation 1. We are not writing the rate law for F because the relation definitely it is expected to be complicated. So, with that our this output, or rather the state variables, we are not thinking about control objective right now. The state variables are V and CA. The input where we have the disturbance Fi and CAI, and manipulated variable, you see for both we have only one manipulated variable, that is F, right. F is the only manipulated variable we have. And the constant parameter of the system is K. So, that is the isothermal continuous starred reactor. Now, the same equation we can extend for non-isothermal reactors. Non-isothermal reactor, again it is a starred tank and continuous. Now, you see the first equation dV dt will be equal to Fi minus F as it is. The second equation, say 1, the second equation V into dCA dt equal to Fi CAI minus CA minus, now let us consider it to be first order. Now, K here is a function of temperature, we use Arrhenius. Right. So, you can write in the assumption Arrhenius model for rate constant is appropriate. Right. So, that is equation 2. Now, when we are thinking of this energy balance, I will write dH dt directly. So, du is dH, and also we consider ideal fluid, that is dH equal to, that is dH is equal to mCp dt, right. So, this is ddt of m is this rho into V, rho into V is the mass into the Cp and Cp into T, right. Next, it is equal to Fi rho Cpi Ti F rho Cpt. Next, there may be, we have a jacket, let us say it is an exothermic reaction, and we are removing heat continuously at a rate of q dot. So, minus q dot plus there will be heat generation, right. Say the heat of reaction as it is exothermic, say heat of reaction at temperature T is del H Rx, right. So, actually del H Rx is what? Heat of the product minus heat of the reactant. So, minus of del H Rx is negative, right, sorry, it is positive. So, this minus of del H Rx, amount of heat which is a function of temperature T, is released when 1 mole of A reacts. Now, what is the rate of the reaction? Minus Ra into V, right, which is dNA dt. So, minus dNA dt. So, this is positive. So, what is the heat generation rate that we want to calculate? So, it is minus Ra into V. So, now we have this assumption that constant specific heat, and with that assumption we can write that rho Cp, here it will be T, or rather V dagger into dt dt plus rho Cp T into dV dt equal to Fi rho Cp Ti, as Cpi and Cp are same, minus F rho Cpt minus q dot plus this minus of delta H Rx. It is a function of temperature, then minus Ra equal to Kc and K equal to K naught into e to the power minus E by RT into Ca into V. So, essentially this rho Cp, if I strike out, this cancels out, divided by rho Cp, here also divided by rho Cp. And dV dt, you see it is Fi minus F. So, it is V into dt dt plus T into Fi minus F, and here on this side Fi Ti minus Ft minus q dot divided by rho Cp plus minus of delta H Rx into K naught into e to the power minus E by RT into V divided by rho Cp. So, finally, this T into F, that cancels out. So, and we shift this Fi into T to the right hand side. So, we will get the equation. Let me erase this part. So we'll get an equation that V into dt dt equal to Fi Ti minus T minus Q dot by rho Cp plus minus of delta H Rx divided by rho Cp into K naught into e to the power minus E by RT into V into obviously Ca will also be there. So that's equation 3. Right. So with these 3 equations for non-isothermal CSTR, we can list the state variables as V, Ca, T. Next it is the state equations 1, 2, this 2 and 3. Right. Then input, in this group we have disturbance. So disturbance is Fi, Ti, Cai, and we have manipulated variable as well. So what are the manipulated variable? F was the manipulated variable and Q dot is the manipulated variable. Q dot is a manipulated variable present in this enthalpy balance and F is another manipulated variable. And constants are K naught, E, then we have this delta H Rx and additionally this much. 3 constants of that system. So that's the model of isothermal continuous start tank reactor. Still we are in the paradigm of lumped parameter systems. So next we will think about a distributed parameter system. So it's a steam heater, right? A double pipe steam heater where through this annular we have the steam at constant temperature and through the central pipe we have a liquid flowing and that is being heated. So why this is distributed parameter? Let me explain. So here we have a double pipe steam heater. Let's think this is the central pipe. And here we have the shell, right. So it's a co-current initially. So it's steam, temperature TST, and here we have the condensate also at the same temperature TST. So that means no subcooling. Of the condensate. Right. Now the liquid, it has got a speed or velocity u, right, and its inlet temperature is Ti or rather T0. we fix our coordinate system from here where it has got the thermal interfacing, and this is z direction. Right. This one is obviously the art direction, the azimuthal direction is theta. Now you see that as the liquid moves in this direction, its temperature progressively increases. So T of the liquid is a function of at least z and time. So when it moves out, it will be T outlet, T at length L, say this is z equal to L, right. So in general, T is a function of R, Z and T. Now over a cross section as this, we can assume small inner pipe dia, so T is invariant with respect to R, and we write that T is Z comma T. Right. Over the specific section, it has got a uniform temperature. Now, how to develop this distributed parameter model? So it is obvious that this can never be a lumped parameter, it's a distributed parameter model. As the temperature progressively increases along the direction of the pipe axis. So we see previously we have applied the conservation equation over the entire control volume. That's an integral volume, right? Because inside this system or the control volume, there is no change of the state variables with respect to space coordinates. But here, as it happens, so we have to consider a differential control volume, right, between Z and Z plus delta Z, right. So over this shell, if we enlarge the view, here we have convective transport, which is U into T at Z. Here or rather this rho into Cp also. Here it is Cp into U and multiplied by A as well. A is the cross sectional area. That's the enthalpy flow rate. So here it's a mass flow rate into Cp into T. So mass flow rate is rho into A into U into Cp into T at Z plus delta Z. Now from this lateral surface we have the heat transfer, and the flux is what? Flux will be U into this P, or rather flux is U into T steam minus T multiplied by the area, this curved surface area, which is P into delta Z, where P is the perimeter. So A is the area of cross section, P is the perimeter. Right. So that's inflow, that's outflow, that's also thermal energy inflow. This is the flow of thermal energy because of material flow, that's also the same. Here this curved surface, through the curved surface we have the flow due to the energy only. This is because of the thermal gradient, there is no material flow. So if I write the conservation of energy, right, so that's ddt of this dm into Cp into T. So dm is rho into A into delta Z into Cp into T, and that's equal to inflow, which is A into rho into U into Cp into T at Z minus outflow A into rho into U into Cp into T at Z plus delta Z plus this flow of energy, which is U into TST minus T into P into delta Z. So, I am not writing explicitly the assumption, so we can actually disregard the variation of Cp with temperature and also of rho with temperature. So, rho A delta Z into Cp, and here it is not ddt but rather del T, because T is a function of Z as well. So, del T is equal to A into rho into U into Cp into T at Z minus T at Z plus delta Z plus U into TST minus T P into delta Z. So, what you can do here, divide the entire equation by this. So, Cp, or rather okay, let us keep this rho as well. So, let us divide it by A delta Z. So, it is rho Cp into del T. Now, A rho Cp U is there. Now, delta Z A cancels out, right, and delta Z goes in denominator. We take the limiting condition that delta Z tending to 0. So, you can write this quantity as minus of del T del Z. So, here we take the limit delta Z tending to 0 plus U into P divided by A into TST minus T. So, obviously, we get that rho Cp within bracket del T plus U del T del Z is equal to U into P by A into TST minus T. So, that is my PDE, as you can see, and we can further simplify because it is a circular in a tube. So, P is equal to pi into D, where D is the diameter and A is equal to pi by 4 D squared. So, if I substitute pi into D and pi by 4 D squared, so P that is 4 into U divided by D into TST minus T, right. So, rho Cp del T plus U del T del Z. So, that is my state model of that system. So, you see that state variable here it is not exactly TZD, okay, it may be TZD we can write, right, that is the state variable, but the output here is different, it is T at Z is equal to L comma T, that is the outlet temperature, right. Input, disturbance and manipulated variable. Here you see we write the initial and boundary conditions that T equal to 0, T equal to this T naught everywhere, right, for all Z, that is the initial condition, and boundary condition is T greater than 0, Z equal to 0, T equal to T naught. So, the disturbance primarily is T naught and at the same time U, and the manipulated variable here it is again okay. So, so these two U's are same. So, let us write it as UT, U of the tube, Right. So manipulated variable is ut. By the same logic, and the constants of the system are tst, d, rho, cp. Now you see this equation directly we could have derived from general energy equation over a control volume. So general energy equation, we know that it is for differential control volume. So it is basically this rho Cp del T plus V dot grad T equal to K grad square T plus Q plus 2 mu d double dot T. This d is the rate of deformation or deformation tensor we have discussed it in heat transfer, and d is equal to grad V plus grad V transpose by 2. Right. So this is the viscous dissipation term. So we drop this, no viscous dissipation, and neither there is any conductive transport, no conduction. Right, but Q will keep as it is. So rho Cp del T plus V, which is U into I cap, U into K cap, because this is a Z, or rather U into Ez cap, because it is cylindrical coordinate, and this grad T has got this Z component as Ez cap into del T del Z. So Ez dot Ez equal to 1, so it gives you U del T del Z. All the other terms of the gradient with respect to r and with respect to theta will vanish, because the velocity vector only having a non-zero component along axial direction. So that's equal to Q. Now what is Q? Q is the rate of heat generation per unit volume. Now there is no heat generation, however, there is a heat means intake, right. Now the rate of the intake over this Z, so Q we are trying to write, so P or rather UT into P into delta Z into TST minus T. So that's the heat intake. Now we will divide it by unit volume, and it will be an equivalent term of the heat generation per unit volume. We are writing the intake in terms of generation. So UT into P by A, TST minus T. So if I write it, rho Cp del T plus U del T del Z equal to UT into P divided by A, TST minus T. So it's the same equation as we have derived here. Right. So this is an alternative strategy by which we can very easily derive this equation for this one dimensional or maybe two dimensional distributed parameter system. So another distributed parameter model may be something called the plug flow reactor. So what is a plug flow reactor? It is a tubular reactor with no axial mixing but with perfect radial mixing. Right. So just like it is a tube. Now in normal tubular reactor, what will happen? There will be axial dispersion, and because of the axial dispersion, the fluid will actually mix to some extent, right? So that dispersion effect can be handled in a separate perspective of reaction engineering called the residence time distribution, right, and dispersion model. So you are not going into that. But here, so to avoid that, basically we idealize the reactor, right? So to how we idealize? We idealize that there is no axial mixing. And how come it is possible? If the velocity is flat, right, it's very high and it's flat, its profile is flat. So there is a flat profile, and flat profile it's called the plug slug piston flow, right. It is possible to achieve at very high Reynolds number, because you see that when Reynolds number increases, in laminar flow we have a parabolic profile, right, laminar. But when this velocity increases, it becomes this more and more flat, right, and finally the extreme is plug flow. Now if I assume the plug flow to take place through the reactor, which is definitely an idealization, no reactor we operate at very high or infinite Reynolds number nearly. Because you see, when we operate the system with infinite Reynolds number, it will become an inviscid flow. And for inviscid flow, we will simply have the no slip to be satisfied at the pipe wall. So just like a step at this pipe wall, it reduces to 0. And throughout the pipe cross section, it will be flat and uniform, right. So that's the idea of plug flow. And because of this plug flow assumption, we can actually avoid the complexity of axial dispersion. So here we have Ca naught, this is Z, only one directional. So and its velocity is also u, right. And a reaction is taking place, say it is A giving product, and rate is minus Ra. So you consider this elemental volume once again between Z and Z plus delta Z. So what happens over there? So U, it's a flow rate, then volume flow rate will be U into A multiplied by concentration Ca at Z, moving out U into A into Ca at Z plus delta Z, and there is reaction taking place. So if we write the unsteady state model, the rate of accumulation, that is del T integral, then this has got a thickness of delta Z, so A into delta Z into Ca, that is U into A into Ca at Z minus U into Ca into A at Z plus delta Z, then minus the reaction minus of minus Ra into dV, dV is A into delta Z, right. So again A into delta Z we take out and we will cross multiply. So this is del Ca del T, it's going to give you UA if you take common, so that's minus of U into del Ca del Z, right, with the limiting condition of delta Z tending to 0, then minus of minus Ra. A delta Z will cancel out. So further we can write that del CA del T plus U into del CA del Z is equal to RA. Right, that's a negative term. And again you see the same equation we can derive from convection, diffusion, reaction equation. So that is del CA del T plus V dot grad CA equal to D into grad square CA plus RA. Right. So obviously the non-zero component of V is the axial directional velocity. Diffusivity is negligible in the axial direction, no axial diffusion, and radially it is well mixed. So we can drop this term, del CA del T plus U into del CA del Z is equal to RA. So it's the same equation as we have derived through shell balance. Right. So now you see, if I think of a steady state equation, okay, let me first discuss about the state variable and input output. So state variable is CA ZT, control objective is CA L comma T, where this is Z equal to L. Right. So input, then disturbance will obviously be U and CA0. Manipulated variable. Actually there is no manipulated variable left, right. So we have to think that U is my manipulated variable. Either U is manipulated variable or CA is a manipulated variable, or CA naught is a manipulated variable. So CA naught is generally considered as disturbance. So manipulated variable will be U. We will go on changing the velocity or flow rate, and accordingly the conversion at the outlet is going to change. So you see here, if I think of steady state, this is U, now it is dCA dZ, because CA is now a function of Z only, it's equal to minus RA, or rather it is minus of minus RA. Right. So dCA divided by minus RA, or minus of minus RA, is equal to dZ by U. So you integrate it from CA naught to CA at outlet, so CA L, and this from 0 to L, right. So it is minus of CA naught to CAL dCA by minus RA, and that's equal to this L by U, which is the space time of this PFI. And finally, if we write it in terms of fractional conversion, that is XA, which is NA at XA equal to 0 minus NA divided by NA at XA equal to 0, right. And let's say it is a constant volume system. So for constant volume system, it's a liquid, so CA equal to CA naught into 1 minus XA, so dCA is equal to minus of CA naught into dXA, and if I substitute, then it will be dXA by minus RA, XA equal to 0 to XA F or XA L, whatever, is equal to tau by CA naught. So that is typically the design equation. We will again cover it. design equation of TFR. Right. So, you see that if I think of a tubular reactor now, where we have it is not a PFR, but rather we have the axial as well as radial dispersion effects. So, you do not have to go by shell balance, basically we have confirmed it. So, we will directly use this equation. A tubular reactor model with Ca being a function of R, Z and T. Diffusion, or rather diffusion in radial direction. It is not radially well mixed, right, because diffusion in axial direction is generally negligible. Okay, let us forget about it. Diffusion in axial and radial direction, both, right. So, there we will have del Ca del T plus u into del Ca del Z, because u is the only non-zero component of velocity. Now, we have a diffusion term and it is a cylindrical coordinate. So, d 1 by r del r of r del Ca del r plus del square Ca del Z square plus R. So, that will be my equation. So, directly we can write it from convection diffusion reaction equation. Okay. So, that is all about the lumped parameter model and distributed parameter model, the overall modeling approach. So, but we have formulated what? The state model, right. And the state models, they are to be solved in order to generate the input output model. But the problem is, everywhere practically we have seen, see just like here, if I consider this u to be a manipulated variable, now u is grouped with a derivative of the state variable. So, this is a nonlinear term typically, okay. U is a function of time, or rather it is not a nonlinear term, but think of the star tank, this reactor or star tank heater. Then in the temperature equation for the star tank heater, for example, we have a term V into dT dt, right. V into V is a volume which is a dependent variable, V multiplied by dT dt, where dT dt is another derivative of another dependent variable. So, they are in product form. So, obviously, it is a nonlinear term. Additionally, we have multiple other nonlinear terms present throughout the equation, and that actually restricts its analytical solution of most of these state models. So, what we have to do? Next, we have to linearize them, okay, based on either this. If it is a single variable, then it is based on the single variable Taylor series, or we have to go for multivariable Taylor series expansion, and that we will discuss in the next session. Thank you.